So the last section we're going to look at in 11.6 is on combinations, permutations, and counting. Counting is pretty much the first thing you have to do if you want to do probability, because probability is the chance that something's going to occur. So usually the way you figure out a chance of something happening is you take like the total number of outcomes that could happen, you put that in the bottom of a fraction, and in the top, you count the number of favorable outcomes. So for example, if you had 5 good things that could happen, and there were a total of 50 things that could happen altogether, you take 5 divided by 50, and that's the chance that the good thing happens. Right? So you got to know how to count how many ways something can happen. Now, because we're going to be looking at counting, we're looking at what's called discrete types of numbers, meaning we're not looking at decimals. Okay? In general, when you're counting the number of ways something can happen, you always get an integer. And when you study like math that pretty much involves integers, which counting does, that's a type of topic that you would do in discrete mathematics. So counting is basically the idea of how many ways can something happen. How many ways could you rearrange the letters A, B, and C? How many ways could you have license plates where there's six characters long, and the first one is an A, and the rest of them are all numbers. Things like that. Then you can get into harder kinds of problems where maybe you look at like a card game, and then you figure out, well, how many ways could I get a straight if there has to be a foreign? Okay, so then it gets a little bit harder. We don't generally get into those kinds of problems here. But you can get into that when you do more advanced counting. All right, so let's see if we can figure out how many different 3-letter codes you could make out of A, B, C, and D. Now, one thing we have to look at in these problems is the order important? Well, pretend it was a password. Is the order you put the letters in to make that code important? Yes. Just because I tell you my password has an A, B, and a C, you don't necessarily know what it is. You still have to try every combination. So let's see if we can list all the 3-letter combinations, but try to do it in an organized way. This is a small enough set. We could list them all. Let's start with, I would start with the 3 letters A, B, C, and rearrange those all the ways you can. So you could have A, B, C. What else could you have? Let's maybe do it in alphabetical order.
A, C, B.
A, C, B. So those are the ones that start with A. Okay.
And then B, A, C.
B, A, C.
And then B, C, A.
B, C, A. Those are the ones that start with B.
And then C, A, B.
C, A, B.
And then C, D, A.
C, D, A. So you could kind of generalize what's going to happen here. If you pick any 3 letters, how many ways are there to arrange a grouping of 3 letters? 6. Now we just have to look at how many ways are there we can pick 3 letters. Well, we could pick the A, the B, and the C. We could also pick the A, the B, and the D, and we could pretty much do the same thing we just did. Or, what else could we pick? We could pick the B, the C, and the D. So if you're getting stuck at like, well, wait, which one is left? Look at the letter you left out. You left out the D. You left out the C. You left out the A. Which letter haven't we left out yet? Yeah. We haven't left out the B yet. So you could do A, C, and D. And for each one of these, you could generate 6 arrangements. So you get 6 here, 6 here, 6 there, and you could get 6 there if you wrote them all out. So how many different ways could you form a 3-letter code using 4 letters? 24. There are 24. Yep. And even for this one, I got kind of lazy. I didn't want to list them all out. I wanted to just kind of look at doing it once and extending that idea 3 more times. And if I said, like, how many ways could you form a 7-letter password, picking them out of the entire alphabet? Well, you don't want to list them all out because that's going to take a while. So counting doesn't mean listing everything out. Counting means figuring out how many ways it can happen. A list is one way, but not necessarily the best. Okay. For small sets of numbers, sure. Big sets, no. Another possibility is to visualize what's happening by making like a tree diagram. So a lot of times I'll make a tree diagram when I'm doing a problem that might involve decisions. Like the person could choose to take road 1 or road 2. And then depending on which road they take there, they have 3 choices from each of those roads. So it's a pretty good way to visualize it using a tree diagram. All right, so let's look at this one. So this one says that an animal is going to perform 2 tasks. And for each task that it performs, it can get one of 3 different rewards. Now, another question we have to be careful about is, when we give the reward out, could we give the same reward again? Like if I have a black marker, a blue marker, and a red marker, and I say these are the 3 rewards. Well, if I give you the red marker for the first reward, in this case, I couldn't give it to you again because I don't have another one to give you. Now I'm limited to just the blue and the black. But for this particular problem, we'll assume that they have like a whole box of each type of reward. So they're not limited. Once they give out one reward, they could give that reward again because they have another one on it. And I kind of want to do it both ways. I want to do it where you can give the reward once and where you can give the reward more than once and just see how it changes the answer. Let's do it first where we only give the reward once. And then we'll see what happens if we are allowed to repeat. So that's what this is saying right here. Each reward is only given one time. Right, let's make a tree. So, animal performs task 1. And after it performs task 1, how many different rewards could it get? 3. So it's either going to get reward A, B, or C. Regardless of which reward it gets, it's then going to perform a second task. So then it's going to do second task.
What kind of animal is it?
This is a dolphin.
Okay.
Yes. Now, after it does task 2, how many rewards are left if each reward is given only once?
Only 2.
There's only 2. So it doesn't matter which reward it got the first time. There's only 2 possible choices for rewards here. 2 here, and 2 here. So what we want to look at is basically how many different paths you can follow in that tree. And that's the number of, what's the question here? The question is how many different sequences of rewards can you get? So you could think of this as like A, reward A, B, and C. This would be reward B or C. How about these 2? What would this be?
A and C.
Reward A or C,
And I and B.
and reward A or B. So essentially it's a problem about arranging letters again. That's all. You just can't use the same letter more than once. So how many different reward pathways are there? 6. There are.
Oh.
So without repeating any rewards, there are 6 different pathways the animal could get. Could get A and B, A and C, B and A, B and C, C and A, and C and B. And getting reward C, then B, or getting B, then C is different. Okay, so getting B first and C second, and then C first and B second, that's a different sequence of rewards. Okay. Now, what about if we had repetition? How many pathways would there be if a reward could be repeated and it's not used up after you give it out? There would be 9. Because you'd have an extra path here for A, an extra path here for B, and an extra path at the bottom for C. So that would change it a little bit. The question in this problem was without repeating, but if you did it with repeating, you get 9. Questions on that? Yeah, downside of a tree, it can get kind of big. So it depends. If you got 15 choices for the first one, and then you got 30 choices for the next one, it's going to be too big. Well, I just answered that. All right, so we're going to look at what's called the fundamental counting principle. And that will help us to figure out how many ways something can happen without listing them out or trying to draw the whole thing out. This is going to involve multiplication. So in the last problem, we didn't have any without the repetition. How many choices did we have for the first reward?
3.
So we had 3 ways of making the first choice. And how many ways did we have of making the second choice for a reward after that? 2. Doesn't matter which reward you picked the first time. There were 2 rewards left over to pick from. So we had 3 ways of making the first choice for the reward. We had 2 ways of making the second choice for the reward. And then if there was a third, reward, we could keep going. We only had 2 to pick from. So if you take the number of ways of making your first choice and the number of ways of making the second choice, which was 3 and 2, and you multiply them together, that will give you the total number of possibilities for reward paths, which was 6 in our case. And this can be extended to as many choices as you have to make. So like let's say, you're getting dressed and you had a choice of 5 different shirts to wear, 3 different pairs of pants, and 2 different pairs of shoes. And you wanted to know how many different outfits could you make. Well, you have 5 choices for shirts, 3 choices for pants, 2 choices for shoes. 5 times 3 times 2. That's 30 different outfits you could put together, just picking random shirts, pants, and shoes. Same idea can be extended to, sometimes you'll see with like food. Somebody had a choice of 5 different entrees, 3 different desserts, and 2 different beverages. How many different meals could they put together based on those different choices? It would be 30 different meal combinations you could make. And that's called the fundamental counting principle. Now, when we do this, this assumes that the choices are independent from each other. For example, if you're getting dressed, the choices might not be independent. If you put on black pants, then you might not wear white shoes with it. Maybe you do. But maybe if you put on a certain color, that would eliminate some of the choices for other things. In that case, then the choices are not independent, because one choice you make for a shirt affects the number of pairs of pants. Then this principle doesn't apply at all. Okay, so the choices have to be independent. Same thing with the reward problem. No matter which reward you picked, it did not matter in terms of how many rewards were left. There were always 2. Or always 2. Okay, so that's called the fundamental counting principle, which would apply to license plates. Okay, we're going to assume that there is no restriction on license plates. Just because the first letter is an H doesn't mean the second letter can't be a Q. Doesn't matter. Another H, yeah. If there was a restriction saying you can't have two letters next to each other that are the same, now it's a lot more complicated. So we're making license plates that have five characters in them. It says that our license plates are going to have 2 letters followed by 3 digits. And it says that there are no repeating letters or numbers. So as long as we take that into account, that's kind of like the reward problem. There were no repeating rewards. You can still use this principle. So let's start with our first choice. This is going to be a letter. How many choices do you have for your first letter? You have 26. Now, it doesn't matter which letter you pick. No matter what you pick, how many choices are left for the second letter?
Right, okay. Sorry, how did you get 26?
Because there's 26 letters in the alphabet, it has to be one of the letters.
Yeah. If it was upper and lowercase, license plates are not upper and lowercase, so that'd be 52, but we're just dealing with uppercase letters. So 26, no matter what you pick, there's 25 choices left for the next letter. So we got the 2 letters, and now we need digits. How many choices for your first digit? You would include 0. Whether they include 0 on license plates, because it could look like an O, we don't know that. But there are 10 different digits you can pick. Now, digits cannot repeat. So no matter which digit you pick, how many are left?
9.
So 9.
And then 8.
And then 8.
Wait, sorry, do we know that it will be number, letter? Or, sorry, I didn't do it right now. Or is that just how we're formatting?
I just went by the order that the problem said. We're going to have 2 letters and 3 digits.
Okay. So,
It doesn't really matter where you put the letters and digits. You'd still have the same number of possibilities. As long as you agree to always put the 2 letters in the same spot and the 3 numbers in the same spot.
Wouldn't it be a different license plate if you
Like order doesn't matter for this one.
So let's see. Yeah, the order.
you could have the same combination of letters and numbers, but if you just moved where they were, like you put the letters at the end and the numbers at the beginning, that's a different license plate.
Yeah, if we switched them to different spots, that would be.
So then it's also how many different ways can you put it?
but yeah,
How did they have there be 2 letters?
has anybody solved that? How many license plates?
Which
can
is
we
similar
make?
to the first one.
So let's do it like this. And in this particular case, there are 468,000. And to simplify it, we'll say that the format has to be like a letter, and then a number. If you were allowed to move the letters around, then yes, it would be different license plates and you could have more options.
It wouldn't be too hard to figure it out if you just moved the second letter down, moved the first letter to the second spot, and moved the second letter down again, and just repeated that. You could figure it out.
Yeah,
You know?
you could basically figure it out by taking this number and then timesing like the different ways you could put the letters. You
I
could
think
put
it's
the
just times 10.
Yeah, you put the letters here, or here. Or you could put them first and third, first and fourth, first and fifth. You just have to figure out all the ways you could put the L's in different spots.
It's kind of scary looking at probability when you realize there's just so many different ways.
Okay, that's going to get a little bit more complicated than what we're going to get into.
So, hold on.
So-
Why is it listed as letter and number when aren't each of them exclusively unique? Even if if they're both letters, don't they still have to be different ones?
They do. That's why this number is 1 less than that one.
So then you also have to interchange them for each thing, correct?
What do you mean? What do you mean? As long as
So
they're
if you had like, I don't know, A and C or something, although they're both letters, you'd still have to change them to get the maximum amount of combinations. So you get AC and then 3 numbers and CA, and then you have to keep doing that.
Isn't that accounted for?
Yeah, that's
It is
accounted
kind
for
of- Yeah.
here. Because if you pick A, then you have one choice gone and you could pick C. Or if you pick C, then that choice is gone and you could pick A.
And
So that's accounted for.
and that's accounted for swapping those in the farm.
Yeah. Yep.
Yeah.
So it's just a matter of, if we were going to get into it, figuring out all the different places you could put the L's in those 5 slots. Right? But I don't want to quite get into something that complicated, and you won't have one like that on the test. But that would be a little more realistic. Okay, so in this case, it follows exactly the order: 2 letters, 3 digits, in that order. Any question on how we got 468,000? Okay. All right. So we've got 8 runners in a race, and we want to know how many ways they can finish. So, like, if you write down the order of all 8, how many different orders are there? So let's say you go through the problem and you pick who's going to finish first. How many ways can you pick the first place person?
8.
There's 8. Now, it doesn't say you can't repeat, but you kind of have to assume that in the problem.
The person
One-
can go first.
Yeah, once somebody
Like,
finishes
what if it's an
first.
8-way tie?
Yeah, no ties. Once they finish first, then we have to figure out how many choices we have left for second and
There's
all the
a
way
tie
down.
because of depth.
I'm assuming you're about to get there, but should we just be lazy and write 8 factorial?
Yeah, it would be 8 factorial. Because then second place, there are 7 choices. 6, 5, 4, 3, 2. And then once you've picked the first 7 places, there's only one way for last place because there's only one person left.
That's really sad when you think about that. I kind of feel bad for that guy.
Oh, hey, maybe it's the other way around. Maybe you take the last place first, and then only one person can finish.
I don't think that's how that works.
It doesn't matter what you do.
So that would be 8 factorial. That's small enough we could do it out, but I'm just going to leave it. So any question on that one? And again, that's an example where the order is important. It makes a difference. It makes a difference if John finishes first and Sarah is second, or Sarah's first and John's second. There's a difference. So in both of those examples, we were able to use that principle I showed you by multiplying together numbers to figure out how many ways we could arrange things, whether we're arranging letters and numbers for a license plate or arranging names in a list of top 8 finishers. Those types of things are called permutations. A permutation is where the order is important. It's a ordering of a specific ordering of elements is called a permutation. So if you were doing like how many combinations could you make on a lock, like for a locker? Well, there's nothing saying numbers can't repeat, and you have to pick 3 numbers to make a combination on like those kind of lockers, and maybe it goes up to 60. So the number of combinations you could make would be 60 times 60 times 60, 60 cubed. That's how many possible combinations there are, or how many technically it shouldn't be called a combination, it should be called a permutation. Even though everyone says it's the combination to their locker, it's really the permutation. Because if it was a combination, the order wouldn't matter. So if you had 14, we'll make it simple, 12, 13, 14. If it was a combination, you could put the 12, the 13, or the 14 in first, and it wouldn't matter. But it's permutation. Okay, so permutation is when the order is important. It's a specific order of elements. How many elements? Well, depends. If it's 8 runners in a race, it's 8 elements. If it's letters on a license plate, maybe it's an ordering of like, if it was all letters, it would be ordering 26 elements. Any question on what a permutation is? So let's look at this one. So this idea I was going to mention, but we already kind of got to it. If you have n elements and you want to put every single one of them in order, like 8 runners in a race, then it is n factorial. If I had 10 different colored markers, and I want to know how many ways can I arrange all 10 of them in all the different color combinations, and all the colors are distinct, it would be 10 factorial. Now, if the colors are not distinct, like let's say you had a red marker, a blue, green, and a black. That's a little more complicated to figure out how many ways you can arrange them, because there is no difference between the 2 red markers. So having a red and a red, or switching red and red, you wouldn't know the difference. Same thing happens like when you want to arrange words, letters in a word. If you had the letters then, and you wanted to know how many ways you could arrange them, it is 4 factorial. 4 times 3 times 2. But if you look at the word that, it's not 4 factorial. And that's because you have the letter T repeated. So switching the T's doesn't make a difference. We're not really going to get into that too much. But I think it would be 4 factorial divided by 2 factorial.
So it wouldn't just be 12.
Yeah, you have to divide when you have letters that are repeated.
Yeah.
Don't worry about it. Now, sometimes we only want to order a subset of elements. That means, like, let's say I had 8 runners in a race, and I want to know how many ways the top 3 could finish. I don't care about anything after the top 3, just the top 3.
Wow.
So that's an ordering of 8 elements, but I'm only looking at 3 at a time. So let's look at something like this. So we have a group of 15 people, and we're going to pick a president, a vice president, and a secretary. That's exactly the same as saying you have 15 people in a race, and you're going to pick like a first place, second place, third place. In this case, the order matters because these are different roles. So think of like, this is president, vice president, and secretary. If you're going to put the names into these slots, and you put, if you change the order of the names, then that makes a difference because that puts them in different positions. So order is important when you're assigning roles to people, just like assigning placement in a race where you finish. It's the same idea. So we can start with any role we want, and we can choose a person for that role. Let's start with president. How many ways can we pick the president?
15.
So it's 15. And then once the president's picked, they can't be used for anything else. It doesn't say that, but I could always clarify something like that on a test. How many ways would there be to pick the vice president? 14. And then the secretary? 13. 13. So it's 15 times 14 times 13. 15, 14, 13, and that gives us 2,730 ways. So that's a permutation of 15 items chosen 3 at a time.
Okay, that's still a permutation. That's not something different.
No, that's 15 items chosen 3 at a time. And because we're only choosing 3 of them at a time, this is called an R permutation, where R is the number of things that you're ordering. So we ordered 3 things out of a set of 15. We didn't order all of them. We only ordered 3 out of the 15. And the symbol that we can use, or the notation we can use to write something like that is 15, the P symbol for permutation, and then 3. And there's a formula to figure that out. Not that it's that hard to do, just 15 times 14 times 13, but that's the formula you can use to figure it out. Does it kind of look like anything?
It's the exact same one we just used. Isn't it?
Almost.
Wait, no, it's not.
Because there's no R.
second. There's no second factorial.
Yeah, there's no r factorial. It's n factorial over n minus r factorial.
Pretty close.
So how many items did we have to pick from? 15. And then we were ordering 3. What's 15 minus 3? 12. And if you cancel 12 factorial into 15 factorial, what's left? 15 times what? 15 times 14 times 13. And that's exactly what we came up with. So this is a quick way to figure out an R permutation when you have that many elements you want to put in order out of the total of that. I'm not going to do example 5 again using the formula. I basically did that right here. Any question on that? All right, let's try this one. How many 5-letter codes? We'll just assume uppercase or lowercase. We don't have to assume upper and lower. But how many 5-letter codes can be made using the entire alphabet? Okay, so we'll say capital alphabet. You can try to do it this way and think of how many ways can you choose the first one, the second one, the third one, and the fourth one. Or first figure out if this is a permutation where the order is important or a combination where the order is not important. What is this? Permutation or a combination? That's a permutation. Anytime you're making a code, the order of the letters is important. How many letters are you choosing from? 26. And how many out of the 26 are you picking? 5. So it's n factorial over n minus r factorial. So 26 factorial over 21. And what's that essentially going to leave me with in the top? 26 times 25, 24, 23, and 22. So there would be that many different ways that you could pick 5 letters out of the alphabet and make a password. Now, you include uppercase, lowercase, and numbers. Well, now you'd have 20 upper and lowercase is 52. Digits add 62. So then it would be 62 factorial over. It'd still be choosing 5. So 62 minus 5 would be in the bottom for the factorial. And then you could add in special characters and things like that too. Any question on that one? Now, if you allow letters to repeat, well, that's easier. It's just you have 26 times 26 times 26 and 26 to the 5th power. If letters could repeat, which in a regular password, usually letters repeating is fine. It's not a problem. Okay, so now the last type of thing we'll look at is a combination. So the idea of a combination is you're looking at how many ways can you do something, and the order isn't important. So one example that you see a lot with combinations is forming a committee. If I want to form a committee of 3 people in here, the order that I pick you to be on the committee doesn't matter because I'm not giving you roles. You're not going to be like president, vice president, and secretary. You're just going to be committee member number 1, number 2, and number 3. You're all equal. So that kind of problem is a combination. Another combination problem would be something like if you were picking prizes, and all you care about is the prizes you get. You don't care. Let's use markers because that's what I get. When you leave here, you go home. It doesn't make a difference if you pick the red marker for the prize first and then a blue, or if you got the blue one first and then you got the red one. You're still leaving with the same two prizes. So if all you care about is like the prize bundle you got, the order doesn't matter. You're still leaving with the same bundle prizes. So you got to look at a problem a lot of times and figure out whether it's a combination or a permutation. Combination, order doesn't matter. I think people mix that up because sometimes they think of like a combination lock, and it's really a permutation lock. You should really think of it that way. Combination, order does not matter. Okay, so committee. You see the word committee? That's a combination problem. Now, this is small enough that we could figure it out. Might be easiest just to assign names as A, B, C, D. And let's say you're going to pick 3 of these people to be on a committee. What's one group of 3 people you could pick out of those 4?
ABC.
You could pick A, B, C.
The same thing I did in the beginning.
Now, BAC is not a different committee. That's the same 3 people on the committee. So there's no listing BAC, CBA, and all that, because the people on the committee don't have roles.
So small.
What's another group of 3 people you could pick to form a committee?
ACD.
Pick A, C, D. So you left out the D, the B. What's the next one?
A, B,
You could leave out the C. And the last one?
B, C,
What is it?
B, C.
B, C, D. Leave out the A. So there are only 4 ways you could form a committee if you're going to have a group of 4 people and you have to pick 3. There are only 4 different committees you could make. Any question why the order does not matter? Okay, so the notation for choosing a certain amount of people out of a group, we did that notation yesterday. If you're choosing 4, if you're picking out of 4 people and you're going to choose 3, 4 choose 3, that is a combination. And the formula for that is n factorial over n minus r factorial, r factorial. We've done that before. When you're dealing with combinations, your answer is a number in Pascal's triangle. Always. So combinations, the answers come from Pascal's triangle. I didn't teach you this notation. That's similar to the one we learned today with the P. But a lot of times I use this notation. 4 over 3. That's a combination. How about 4 over 4? What would that be? 1. Because that's the last row, last column. Well, 4th row, last column in Pascal's triangle. And the last column is always a 1. If I had 4 people and I want to choose all 4 of them, well, there's only one way I can do that. I pick all 4. Same with if I had 4 people and I don't want to choose any of them. There's only one way I can do that. Don't pick anybody. Any question on this formula? Okay. So was that? Yeah, we were just about done. So we'll look at the last problem, the last 2 problems tomorrow. We were just about done.
Math.
Okay, so that's the homework for tonight. Tomorrow will be review day, so we'll go over everything that people have questions on. And there'll be a study guide on Edgelastic. No, not on Edgelastic, on Schoology for the test on Friday.